Now, this RC time delay, so I don't need to tell because you have already studied RC or LCR network. Now, from transistor, where you are getting RC time delay. So it is very clear, no? So you have a transistor. You have a transistor. So this is gate oxide, right? And you know this forms some sort of capacitor, no? That you know. So this is source, this is drain, this is gate. So this sort of capacitors you form over here, correct? So that you know, that is called the gate capacitor or oxide capacitor. Similarly, so when you are connected, the gate is connected by some wire or metal contact, no? So metal also is having some sort of resistivity, which you cannot avoid. 10 ohm, 20 ohm, 30, 40 ohm, whatever resistance is, it is there. So that means this also is there. So that actually, so this sometimes give you the RC time delay. Okay. Okay, RC time delay. There are some other type of delay. It's called the on resistance delay, so which I'll discuss. But one thing it is clear, you have a capacitor. Capacitor means it is holding some charge. So charging and discharging, like if you already started inverter, no? So it totally depends on the how fast your capacitor is charging, how fast its capacitor is discharging. So it is limited by a RC time delay, right? So that actually also kind of a limiting factor for you. Okay, but that somehow you can manage because manage means you cannot avoid, but you can calculate, predict. There are few more things like routing capacitor. So what I'm telling that devices are interconnected by each other via metal lines on silicon or silicon dioxide. These wires will have a capacitor with this substrate. Suppose you have a one capacitor over here. So what I'm trying to tell you, suppose you have a one transistor over here and another transistor over here. So you need to connect this transistor to this transistor, right? You know that inverter, your gate is connected, correct? Whatever. So that means, so what I'm trying to see, like this wire has to go and has to connect, correct? So it's not about the one inverter. There are plenty of inverters are there. Lot of metals are there in your VIA system. So these two metals are there and they are actually passing through parallelly or whatever way. So they also can act as a capacitor, right? So that's a two metals line, and definitely these metal lines are actually passing through your substrate on oxide, on some dielectric media, on some insulating medium. So definitely it is having some sort of dielectric constant. So you ultimately you see that is a parallel plate capacitance things are happening, which is also a great limiting factor. What is transit frequency? We'll see the transit frequency here. So you know that that is my transit frequency. Frequency is equal to 1 by 2 tau t. Tau t is actually transit time. So here actually L is the length of the velocity. Okay, fine. What is that? Yeah, tau t is actually transit time. Tau t is transit time. So L is the length, V is the velocity. Correct. Now, so this is the one thing. Please remember. Similarly, also remember V is equal to mu E. Your velocity is proportional to mobility and electric field. You know this part, right? Now, if you know the V is equal to mu E, so for a transistor looks like this one. You can write what is my field. Okay, if it is a length L, so what is the electric field? VGS minus V threshold, because definitely that is your electric field you are applying, right? And that is it. And that definitely I'm thinking about, let's you think about saturation region. You remember your saturation region VDS is equal to VGS minus V threshold. So I don't need to discuss this, but you already know. So here actually same thing, I have VGS minus V threshold divided by L. Now, then what is my tau T? So this V I have calculated, and so I just write, so tau T is equal to L by V. So V actually I give it, write it here. So you will get L square mu VGS minus V threshold. Now here I will see is the angular frequency 2 pi ft. Just 1 minute. So this is my angular frequency. You see that part? So 2 pi ft, and ft is equal to 1 by 2 pi tau t. So you put all these things, so you will get tau t is equal to, sorry, wt is equal to mu vgs minus v threshold by L square. Okay. Now what we are doing, we are actually doing same thing. So we are actually multiplying Cox by into W and dividing Cox by W. Cox into W. So the red color we are multiplying, so same thing, red color things we are dividing also from this. And if you do these things, you will get, so same manipulation we are doing. So here actually L square is there. So I put L, one L over here, another L outside this unit. Okay. Similarly, Cox W I have taken out. And this is nothing but GM. So this factor, if you remember this factor, this factor is GM and divided by L Cox by W. Now, what is L Cox? Cox, you know, the capacitor per unit area, W by W into L is the area. Now, width into L. So that is actually total input capacitor, GM into Ci. So your cutoff frequency is depends on your transconductance and input capacitance. What it means? It means like if you want to increase your transconductance, your GM has to increase. Okay. Similarly, your Ci has to decrease. Input capacitor has to, definitely. The moment you decrease your input capacitor, so RC time delay also have an effect. So all these things you know. So ultimately, what we are saying that Ci has to decrease. Very important. That means what? That means what I'll tell you later, but Ci has to decrease. But here you can see Ci is Cox into W by L, W into L. Cox, the capacitor, the oxide capacitor, always want to have a high value. Why? Because if you want to make it high value, you will have a very good gate control. Very good gate control, right? The capacitor value has to be very, very high. We'll see. But here, to operate at frequency, suppose 100 gigahertz or more, you need to have this whole unit. This whole unit has to be very low. Then how we can make it very low? We have to decrease W into L. What it means? If you try to make W and L, that area, that means you should go to short channel device. So compound semiconductor deals with short channel device as well. Not like a CMOS. It's not a proprietary of CMOS. Compound semiconductor also wants to have a short channel device if you want to operate at high frequency. Okay. So that is what I am saying. So what I am trying to, so ultimate our thing is that if you want to have a WT, it's high. So what is that? Your GM, your transconductance. Okay. Your transconductance should be high and CI should be low. But if you want to CI should be low, you then W into L has to low. Short channel device. You are going to study the short channel device for CMOS device for by Dr. Sheena ma'am, but you are going to study here also short channel device, but not that great details because the physics is more or less same. What actually Dr. Sheena is going to teach you. Now, what's about so another parameter factor? You know that this is called the so transit frequency. We understand. Okay. So transit frequency is WT into GM by CI. What's up the cutoff frequency? So this is such a simple, and you know, so cutoff frequency always people, so transit frequency always device people think about. So I mean, like those people what discussing or consulting device nature of a particular structure. So the people are also discuss about the transit frequency. Cutoff frequency is kind of proprietary of those kind of group of people who are discussing about the circuit nature. Okay, small signal line. So here as this very small signal model, very of transistor, and you see your IL, that is this part, GM into VI, you know that part. And what is VI? VI is the voltage drop across this capacitor. So I in, so suppose there is a I in current. Okay, so GM I in by JWCI, correct? This is your VI. Now, what is your cutoff frequency in circuit nature? You know that part when the input current and output currents are same. That is the cutoff frequency, right? So that is what I'm doing. That's what I'm doing here. I1 by I in is equal to GM by here. And if you want to make it 1, so what is that? You will get WT. Yeah. Don't be surprised. See the same result. That means WT is the transit frequency. Same write a cutoff frequency also. So what I'm trying to tell you, those group of people who are always telling actually cutoff frequency of a circuit nature, okay, and those group of people who are much more worried about the transit frequency of a device, they are actually considering both same thing. Because ultimately thing is that you have to have a good GM by CI ratio, right? So transit frequency and cutoff frequency, in this case, it is same, right? So there is no difference. There is another thing is the on resistance. What is on resistance? That actually gives you a lot of like a time, RC time delay and all these things. So on resistance has to be studied nicely. So what is my on resistance? You know that this is my structure. Okay. So this is a typical ID VGS structure of a particular VGS value, correct? Now, what is my on resistance? So on resistance, definitely you are thinking about very low value. Suppose, because you can think about, you can see that up to this level, the IV characteristic kind of linear. Right? And if you want to have a good speed of circuit, your on resistance should be low, right? You know that part. I think someone is actually already studying Dr. Emmanuel Close, right? RF frequency or RF integrated circuit. So you know that part. So this is very important. So my R on should be low. Now what is my on resistance? So you go to that. This is actually our fundamental expression. I is equal to mu Cx W by L into Vgs minus Vthresh into Vds minus Vds square by 2. Sorry, I have missed this part. Okay. Now here actually I am discussing very low Vds. Right? Because low VDS means below my threshold voltage, because after threshold voltage it is actually going to saturate. So what we have to study? We have to study below threshold voltage. Okay. So because from this structure, from this curve, you can see below threshold voltage your curve is kind of linear. Okay. So in that case, what I can assume analytically, my VDS is very, very low. So in this case, what will happen? The same thing I'm writing, VDS, VGS minus threshold voltage. And then I can neglect, since VDS is very, very low, so I can neglect this part. So I am ending up with this part, mu C of W by L, VGS minus VDS. So this part actually I neglect. Now del ID by del VDS, what is that? So we get this value, mu C of W VGS minus V threshold. So del ID by del V. So what is my resistance? So del VDS by del. So my resistance is, so this is my resistance, correct? So what you are getting ultimately? Ultimately, you are getting a fantastic thing. So here also I'm writing here. So WT GM Yox. Okay. So we got, and this is actually R on resistance. So you see that we have a 3 part that we got. Okay, 3 limiting factor. One is actually ultimately your cutoff frequency or transit frequency has to be GM by Cx into W by L. Now W into L has to be low, short channel, right? So that is the one concept, short channel. So we have to, but we'll always see that we'll go to L as equal to low. Short channel means like we are going to decrease the W rather than decreasing W. We are going to decrease the L rather than decreasing the W, but it is a kind of ratio. If required, we have to decrease W also, right? So, and you know the CMOS scaling rules, if you want to increase the L, you have to increase the W also. Sorry, as per the CMOS scaling rule, if you decrease L, you have to decrease W also. Same thing over here also. If you try to decrease the L, if required, you have to decrease the W also. But then only you can WT has to be go high. What's about GM? GM has to be very high. Now what is the formula of GM? So GM you can see mu C of W VGS minus V threshold into L. What it means? It is another great things are telling you. Look at. So here you have to take a very right judgment. Look, it's not so blindly. So first of all, if you want to have a high GM, because you want to have a high threshold voltage, threshold frequency, so your mobility has to high. What is the mobility of silicon? Below 1000. Here is the point where the moment you want to have a mobility high, mobility is a kind of factor. It is a kind of intrinsic properties of a material. So you cannot do much better by changing the structure. So you have to choose a different material because silicon mobility is less than 1000 centimeters per volt second for the electron. So what is the best choice for us? Go for compound semiconductor. For an example, I'll show you tomorrow. The gallium arsenide mobility is 8500 centimeters per volt second. 8,000, and where silicon is actually, for an example, I am taking 1,000. So gallium arsenide or gallium nitride or all these compound semiconductor around 7-8 times higher mobility. So if since you want to increase the GM, so you should have a high mobility zone. So definitely that is the one zone. So if you want to have a high mobility, you need to have a compound semiconductor. Okay, because compound semiconductor mobility is very, very higher than silicon. So suppose you want to operate your device at 1000 gigahertz or 600, 700 gigahertz, silicon is not a good choice for that. You have to replace the silicon with a compound semiconductor, which is gallium arsenide or gallium nitride or some other material, which we'll see later, indium phosphide. We'll see that part. Look at the very conflict and confusing things. W, if you want to increase the GM, your W has to increase. But what I told you here, look at here. Your W and L has to decrease so that your WT, that cutoff frequency has to decrease, has to increase, right? If you want to increase the cutoff frequency, your W into L, that is the area, that is the cross-sectional area, has to be decreased, correct? Now, if you want to have W has to increase, W has to decrease, right? But if you decrease W, then GM will also decrease. So that you cannot do. So what is the idea? Idea is to don't do much on W. Don't do much on the W, because if you change little bit of W, your cutoff frequency, because your cutoff frequency is actually depends on GM, and GM is also proportional to W, right? So if you decrease W, your GM also decrease, right? So don't touch if you really need it. Don't touch W if you really need it, rather than you play with the L. So you need to have a L low. So if you want to have a low L, your GM is high. So that means your transit frequency is also high. Similarly, you see that my W by L ratio has to also decrease. So L also, this is also supporting that low C in. Right? So you decrease L. So you decrease L. If you really, which I'll tell you later what is the problem. So when we have to touch W, but you see that if you don't, try to avoid avoid any kind of manipulation on W as long as possible, if it is permissible. Okay, it's a preferable choice. Okay, rather than you play with L. Okay, so if you play with L, so what is the things are going to have? So you'll have a high GM. Now you can say, suppose I have a particular structure of my semiconductor, and in this case, I have a high W. I have achieved like 1000 gigahertz, but my operating frequency is suppose 700 gigahertz. Then how to reduce it? Means not operating. Suppose you, based on your device or based on the basic things, you have what you have achieved theoretically 1000 gigahertz, but user is asking a device of 700 gigahertz. So thing is that then you play with W into L ratio so that you can bring 1000 to 700. So that is actually crucial part. It's a design. You are going to design. So forget about the semiconductor device fundamental last semester. Now here people are asking about a design. So theoretical limit of a compound semiconductor give you around 1000 gigahertz, but user is asking a device of 700 gigahertz. So that means you have to reduce 1000 gigahertz to 700 gigahertz, the operating frequency. How to do it? You then only you play with W. Because the W by L, W into L, that multiplication factor, the cross-sectional area actually manipulating your the cutoff frequency. So please remember, when you try to design a MOSFET, which we are going to do this semester, you have to be very careful about this W into L ratio, or whatever, WL multiplication factor. That actually gives you that what is the operating frequency. Now you can ask like, okay, but that means we got a theoretical limit of 1000 cut. It is, we are reducing it, and that is the advantage of compound semiconductor. Compound semiconductor gives you like high limit, large limit. Okay, then you can reduce the your operating frequency. So, but suppose somebody is telling you, okay, I want to operate my transistor at 2000 gigahertz, but theoretical limit is 1000 gigahertz, a particular structure, particular device. So that means you can say, see, because my theoretical limit is 1000 gigahertz, so I cannot operate my transistor at 2000 gigahertz. So it's not possible. But if somebody asks you to reduce the frequency from the theoretical value, you can do it. And that is the key point. Silicon theoretical limit starts over our 30 gigahertz. Okay, where silicon for gallium arsenide, people are even thinking of terahertz range. Forget about gigahertz. People are thinking about terahertz range. So here is the key factor. So silicon is kind of operating frequency 30 gigahertz. So you can operate anything down to 30 gigahertz, but you cannot go up. Whereas compound semiconductor, suppose 1000 gigahertz, so you can operate your transistor anything, any frequency down to 1000 gigahertz, not upper than 1000 gigahertz. So it's very important to you see the high frequency limit, right? So here actually compound semiconductor gives you high frequency limit. And how to achieve the high frequency limit? You have to have a structure where you will get a high mobility. But if you want to have a high mobility, you have to think about it should not suffer any kind of collision. Very, very important. You need to have a high mobility where you want to avoid any type of collision. You can ask how it is possible, because my electron is flowing through a transistor, flowing through a material. The material has a lot of defects. You cannot avoid all kind of you cannot go have a electron transport without scattering. It is possible, and that is why HEMT comes, high electron mobility transistor, which I'll be discussing at the end of this electrical part. Okay, so it is possible that electron is flowing in a particular material without having any type of collisions. That means no scattering. That means it is like a bullet. Okay. So this type of structure we are going to discuss over there. So thing is that if you want to operate a high frequency, you should have a high mobility. Number one, you should have a low L, that is a channel length should be low, and then you just think about W based on your applications. Okay. So that is actually ultimate thing. So next, all our discussion will be focused on how to achieve high GM and low L. Okay, for a particular structure. And structure is what? Structure is Schottky diode. Structure is MOSFET, metal semiconductor field effect transistor. Structure is our what is called HEMT, high electron mobility transistor. Okay, so I'm stopping over here. So tomorrow we are going to discuss about compound semiconductor, like type of compound semiconductor. I have to give a details of compound semiconductor, no? Which I have not touched yet. So which I'll be discussing tomorrow. Okay. Thank you. So any question?
Sir, what is the significance of transit frequency? Why we calculate transit frequency or cutoff frequency?
So transit frequency means how fast your electron, the moment you give a voltage, how fast your electron can start, starting from source can reach to your drain. Sorry, yeah, source to drain. How much time it needs to like travel this distance. You'll see that that plays a significant role, because that actually gives you the R on. Because R on, the on resistance of R is also a very limiting factor. Okay, for your operation, high frequency operation. Okay, this transit frequency actually is related to the R on. Okay? If you have a very high like if you, the moment electron released from source and immediately reach to drain, your Rn is actually very, very low. Okay, so that means the, if you have a high frequency for to reach electron from source to drain, your Rn is actually going down or down, which is very essential requirement of your RF operation or high frequency operation.
Okay, sir.
And cutoff frequency that you check, you understand that you check with the circuit part, you can find out. No, I think you can find out, Dr. Emmanuel. Okay.
Yes, sir. Yes, sir. Thank you, sir.